Hey everyone. If you agree, I'd like to take you to space again tonight. Have you ever heard about Project Orion? There is a space vehicle called Orion, currently under development by the NASA and the European Space Agency, and it is expected to be operational in a few years. But the Project Orion I will talk about tonight is a completely different thing. It sounds a bit crazy, maybe, but it was a real space exploration project from the 1950s and 60s, designed for interplanetary exploration with ships powered by nuclear bombs, and even the project of an extra-large ship, some sort of ark as big as a city, that could have traveled to other stars. Of course, it sounds little credible 60 years later, because none of this happened. But it was much less crazy than one could imagine, and actually rather credible on a technical level, and yet it was never built. But this is what I'm going to talk about tonight, and it is a good opportunity to also talk about spaceship design, propulsion in space, and how to survive in such a hostile environment. So all you have to do now is relax and have your headsets on and get ready to take off to space. As usual, you're not requested to have any knowledge of astronautics to understand what follows, and don't worry about the visuals neither. You won't need them to understand. So if you wish, you can just close your eyes and follow along with my voice. I'll put links to other planetary and scientific videos in the description. So let's get started now. Sometimes it can be a bit depressing when you think about traveling to space and you realize all the hardships involved. The environment up there is incredibly hostile for human beings. There is no air, so we can breathe. There is no pressure, so we need a pressurized suit or a ship to survive. The temperatures can be extreme for us. It can be very cold or very hot. For example, the temperature around the International Space Station, just a few hundred miles above our heads, is minus 250 degrees Fahrenheit. This is enough to almost instantly freeze a human body. But if you're not in the shadow of the Earth, you are directly exposed to the sun, and the sun rays are not filtered by the atmosphere like on our planet, so you can warm up to the temperature of a kitchen oven very quickly. Our bodies are just too fragile for space. But leaving aside the difficulty of staying alive in space, the other complicated thing is the distance and the need for very powerful propulsion. Even with the best rocket propulsion available today, a trip to Mars or Venus takes months. And these are just our neighbors in the solar system. Reaching the limits of the solar system takes years. And beyond that, traveling to another solar system would take tens of thousands of years. What Project Orion did was trying to address this challenge of the distance. It was born in the years when space exploration was just starting. The first trip to the moon was being prepared. It would take place 10 years later, and there was considerable ambitions and hope surrounding space exploration. Actually, the question back then, in the 1950s and 60s, was not really whether it would be possible to go to Mars or Venus or even the moons of Jupiter, but rather how to do it and when. And given the distance and the costs, a lot of attention was paid to propulsion. Now, what was the most cost-effective and compact source of energy known in the 1950s? It was nuclear energy. And that's the basis of Project Orion, how to use nuclear energy to power a spaceship. You know that many engines are based on combustion, including most car engines, unless they are electrical, and rocket engines. In a combustion engine, the core of the system is a combustion chamber. In the case of a car, it is a cylinder with a piston. There are several of them, but they're identical. You know that to get combustion you need a fuel and an oxidizer. So in a car engine, a mix of air and fuel, generally gasoline, is injected into the chamber. In a four-stroke engine, these are the ones used in most cars, the piston moves up and applies pressure to the mix of air and fuel. There is a plug located in the upper part of the cylinder that produces a spark, and the spark makes the mix detonate. This small explosion generates heat and gases in expansion that push down the piston and give it mechanical energy that can be transmitted to the vehicle through mechanisms. Then burnt gases are evacuated through a valve, the piston moves back up, and so on, so that the car gets constant mechanical energy. A rocket engine is based on the same concept of turning chemical energy into mechanical energy. Except in this case, in a sense it is even simpler, because the combustion chamber is opened and it has a bell or hourglass shape. The fuel is introduced inside the combustion chamber together with the oxidizer. The combustion liberates hot gases that are expelled inside the nozzle, and they provide a thrust to the ship, the rocket, the missile the engine is attached to. Now, to make them more efficient, rocket engines are shaped like a hourglass or like a tube pinched in the middle. This pinch helps collect the energy from the combustion and accelerate gases in the combustion chamber, which provides more thrust for a given quantity of fuel. So conceptually, rocket engines are actually easier to understand than the average car engine. There is no piston that needs to transfer the energy to the wheels through more mechanisms. But the engineering and the monitoring of a rocket engine is way more complex, because they are made to deliver much more mechanical energy for a shorter time, and they use way more fuel at once than a car engine. So they need a perfect mix of fuel and oxidizer. And when it comes to bigger engines, like for rockets, they need a cooling system so that the sides of the combustion chamber and the nozzle don't start to melt because of the heat or break because of the pressure. Actually, rocket engines have a much shorter lifetime than most other combustion engines, and except in some cases like the space shuttles or the SpaceX rockets, they are most of the time disposable. So you understand that theoretically, as long as hot gases are generated in an explosion and provide a thrust, you could make whatever you want detonate in a combustion chamber. So why not an atomic bomb? And in theory, assuming that could be done, that could be extremely efficient to propel a ship, because the storage of fuel would occupy much less space than the traditional rocket propellants, and the energy liberated by the explosion could be extremely important. In the first milliseconds of an atomic explosion, the temperature at the center of the fireball reaches millions of degrees. And gases, because of this very high temperature, expand between 3,000 kilometers per second and 30,000 kilometers per second. This is 1 and 10% of light speed, respectively, and way more than in any conventional chemical explosion. So you can see the appeal, because if we can use the thrust provided by gases that expand at several percentage points of light speed, that would theoretically put all bodies in the solar system at just a few hours from the Earth. Now the problem is that no realistic combustion chamber could ever be strong enough and large enough to contain a nuclear explosion and orientate the flow of hot gas through a nozzle. We just don't know of any material that can withstand that kind of temperature. Or alternatively, the combustion chamber would need to be several miles wide, which is not realistic. But maybe if we are just a bit less ambitious about using all the energy from the nuclear fireball, there could be a solution to this. And that would be just to drop the bomb behind the spaceship we want to propel and use the blast to move. Even with a fraction of the energy liberated by the nuclear explosion, that might be enough to accelerate the ship. And even though it would take probably several explosions and a very precise management of the acceleration, it would still be possible to reach several percentage points of light speed. That may sound a bit silly because it's actually very simple, theoretically, but it's really credible. At least it was serious enough to be studied. And this propulsion concept, an external detonation, was the base for Project Orion. And you're going to see that it was one of the most ambitious and maybe mind-blowing space travel projects to be actually studied and taken seriously. So what is it? It was developed by a small group of American engineers between 1958 and 1963. The initial idea was to develop this propulsion system based on nuclear power that could make high speeds in space possible and would allow the exploration of remote parts of the solar system, and even maybe travel to other systems several light years away from the Sun. From there they developed sketches of spaceships, and this is what an Orion ship would look like. There are two main sections. At the front, the payload, with passengers, cargo, all sorts of equipment they need. And then there is the propulsion section, designed to withstand the pulse from nuclear explosions. In between, there is a section where hundreds of nuclear charges are stored at the beginning of the journey, and they would have been dropped one by one to detonate behind the ship. So the propulsion module is not an engine, it is passive. It is just designed to absorb the push from the nuclear blasts, and it is made of a pusher plate with a hole in the center to drop nuclear charges, and behind the pusher plate various sections of shock absorbers. There are shock absorbers or dampers because this ship design would have had to deal with the very powerful thrust from a nuclear explosion. Theoretically, it could maybe have reached several percentage points of light speed, but if you do that very fast, the crew is going to be killed almost instantly. Reaching 0 to 1% of light speed in a few seconds would represent thousands of Gs for the crew on board. And this is way too much for human bodies. You know that the Gs are a measure of acceleration for a body. For a person, they represent the additional weight sensation when you accelerate or decelerate. An acceleration of 1 g, be it vertical, horizontal, or on the side, means that you feel double your weight. Just to give you a few benchmarks, when you are on a train departing, you take 0.1 to 0.2 Gs during the acceleration phase, which means that you feel your weight is increasing 10 to 20%. Still, that's a relatively soft sensation. A standard jet airliner is about 0.4 Gs when it is accelerating and taking off from the runway. In roller coasters, you can experience all sorts of Gs, of course, including negative Gs when you decelerate, but the most extreme are between 2 and 3 Gs. And you are already requested to be in good physical condition to minimize risk. This is probably the highest level of Gs that the general public can experience. Higher Gs are for professionals with training. A Formula One pilot, for example, can experience up to 5 lateral Gs in curves, and fighter jet pilots can sometimes reach up to about 10 Gs. For someone without training, this means a loss of conscience and possible internal injuries too. It is estimated that death becomes almost unavoidable above 50 Gs. And this means that for our passengers on board the Orion ship, the acceleration needs to be progressive and more linear. Given that the acceleration is going to be progressive, it means it needs to last, and they could probably not absorb more than 2 to 3 Gs at a time. And that means the acceleration could last several days, if not weeks, before the ship reaches its cruise speed. There are two mechanisms to dampen the acceleration. The first is to use smaller nuclear charges and more of them, and the other is the propulsion module. This section is made of various shock absorbers behind the pusher plate. The plate receives the shock wave, and the dampers smooth it and make the acceleration more progressive. Now this is a digression, but this issue with the Gs, when a spaceship accelerates, is something that is generally completely disregarded in sci-fi movies. Maybe for good reasons, because that could be a drag to the pace and the storyline. But sometimes they show the passengers going to a pressurized chamber or some sort of cryogenic box, but this would do nothing to solve the G's problem. I'm all about suspending disbelief, and I don't want to sound like Kathy Bates in Misery, but this is a major unrealistic point in many sci-fi movies or TV shows involving spaceships. I have watched one good sci-fi TV show that makes a really good job at presenting things realistically. It is called The Expanse, and I highly recommend it, including for the plot itself. It's a bit like Game of Thrones in space. So, returning to our topic, the problem with the acceleration and at the end of the journey, the deceleration could be manageable, but it would extend traveling time considerably. There would need to be an acceleration and a deceleration phase that could last weeks or even months maybe, in the case of a very long-haul journey. when approaching its destination, the ship would need to flip side and detonate more bombs ahead of the pusher plate to slow down. You don't lose your speed spontaneously in the void because there is no friction with air. Now, imagining a ship would travel to the borders of the solar system, it would actually lose part of its speed before reaching destination because of the gravitational pull from the sun. The sun tends to make you decelerate as you move away from it because of its powerful pull within the solar system. But in any case, more blasts would be needed anyway to monitor the deceleration. Another problem with the propulsion in this project that would need to be addressed is the exposure of the crew to radiations from the nuclear blasts. This is why there is a disc-shaped section of the ship between the propulsion section and the payload that would serve as a shield for radiations. And on top of this, the habitable module would have included anti-radiation boxes for the crew to take refuge during the acceleration phase when many bombs would have been detonated. The fuel section, which is between propulsion and payload, would have been made of various stacks of nuclear charges. And now, to optimize the use of the plasma wave when the charges detonate, there would have been special nuclear bombs. It is actually possible to influence the shape of the plasma wave in a nuclear explosion based on how the reaction mass is arranged inside the charge. And what we want in that case would be a cigar-shaped kind of wave, so that as much thrust as possible could be transferred to the pusher plate. And this is possible giving a disc shape to the reaction mass inside the bombs. Obviously, there is still an elephant in the room with this propulsion method, and it is radioactive contamination. I'll come back to that later. But if we ignore the environmental issue for a second, the efficiency of this propulsion method can be theoretically very high. What you aim for in space propulsion is the maximum thrust for the minimal energy spent and minimal mass of fuel. In engineering, this is called specific impulse. Project Orion had, theoretically, the highest specific impulse ever conceived in a space exploration project, including, as of today, way higher than the actual space propulsion systems. With such an efficient propulsion, it becomes possible really to imagine very large ships, including generation ships that could have traveled to other stars and would be several million tons heavy. Actually, there were 3 sizes of Orion ships that were envisioned in the last phase of the project. A small one for exploration. It would have probably been the first one built if the project had not been abandoned. It would have carried about 500 bombs, and it would have had a diameter of 17 to 20 meters and a mass of 300 tons. This is not that small. The Apollo ships had a mass of 45 tons, and the International Space Station today is slightly bigger only, at 400 tons. Then there would have been a second size, a mid-range Orion, for interplanetary travel and freight, 40 meters in diameter, and 1,000 to 2,000 tons heavy, with 1,000 bombs on board. And finally, the Super Orion, which would have been an interstellar arc, 8 million tons, 400 meters in diameter, and it would have carried 1,000 bombs, but extremely heavy bombs of 3,000 tons each. No bomb that big were ever detonated on the Earth. And just to give you an idea, 8 million tons for a man-made structure is 180 times the Titanic. The project was finally shelved in 1963 as a consequence of the worries surrounding nuclear weapons and radioactivity. After the Cuba crisis in 1962, talks began between the USA and the USSR to curb the proliferation of nuclear weapons. And this is really what killed Project Orion. Actually, there are two major problems with the use of nuclear charges in space and on the Earth. The idea of detonating multiple nuclear bombs in space sounds bad, but it's not as problematic as one could imagine. Since the 1950s, we have realized that space could be intensely radioactive already, especially around the Earth in the Van Allen radiation belt that surrounds our planet. Detonating nuclear bombs in this environment would barely contaminate it more than it already is. What reduces radiation on the Earth are the Earth's magnetic field and the atmosphere. They deviate and they filter radiation. So, provided the ship doesn't start dropping bombs too close to the planet, there would be no measurable impact on radioactivity at the surface or even including at the periphery of the Earth. But still there is the problem of how to send to space the ship itself and the bombs from the surface. The initial project envisioned taking off also using nuclear charges. The ship would have needed about one detonation per second during the takeoff phase, and so this means dropping a few dozen nuclear bombs in the atmosphere, each one with its own fireball and a nuclear mushroom just for one ship. And this is obviously completely unacceptable for the environment. In the 1950s, there was already a good understanding of the effects of radioactivity on health, but the preoccupation for the environment was not what it is today. But still, there was more than enough to dismiss this project of taking off with nuclear power. One solution could have been to send the ship in pieces to space using conventional propulsion. In the 1960s, the Saturn V rocket, the one that later sent the Apollo missions to the moon, was already in development, and it could have been used for heavy payloads such as these ones. But even though this would have been feasible, the bigger problem is how to send to space the nuclear charges safely. If anything goes wrong with the rocket, nuclear charges could fall back to Earth and be destroyed. The risk is not so much that they would detonate, because a nuclear bomb that is disarmed cannot turn critical and explode. It is more the pollution from tons of plutonium or uranium, highly enriched, being disseminated everywhere in the environment. And it could turn into a complete nightmare if the rocket explodes in altitude, because the dissemination of nuclear waste could cover a huge area. No solution to send so much nuclear material safely to space was ever found, and that remains true today. We couldn't do that. So ultimately, this is what caused Project Orion to be abandoned. But still, when it was elaborated, it was actually quite realistic on many counts. The propulsion system makes sense. The performance would have redefined space travel, and almost all the materials and equipments necessary to build the ships were already available or soon to be available. But the problem that could never be overcome was the nuclear risk on Earth, which could not be reduced to an acceptable level. And this, together with the political context that turned against the race to nuclear weapons, that led to the abandonment of Project Orion. In 1963, it was shelved for good, and it seems unlikely to be revisited now, at least in the foreseeable future. I must say, when it comes to space, I have a bit of nostalgia for the 1960s, because it was a time when many people were not afraid of dreaming big, sometimes too big, obviously, but it is this drive and the space competition that produced the Apollo missions to the moon, the sending of probes to the limits of the solar system, the improvement in rocketry, satellites. It gave us space stations too. And I am glad a bit of this imagination and ambition seems to be back today with SpaceX, with the projects to return to the moon, or to send manned ships to Mars, or even mining in space in the longer run. So this is all for today. You can now sleep tight, and I'll speak to you again soon. Goodbye.